Ah. Double math every day. I should get this shout out here early so that you get very few so early shout out equals for you got 4. Dr. Young's lab. What a great tight-knit community we've got here. Filled with positive feelings. Oh my god. Yeah, healthy. It's healthy. Healthy relationships. Yes, absolutely. That's an advanced professor technique. There are many of those. Secrets. Trade secrets. Let me type that out for you. Overheads you speak of. All right, students, welcome. Go ahead and be seated on your couch or whatever, and get some food if you need it. Here we go. We have our typical Monday, Wednesday, Friday 45-minute lectures to cover the same amount of material. Yay. All right. So, let's see. Anything I need to say beforehand? Oh, wait. What is that I'm hearing? I'm getting a breaking news alert. No exam on Monday because of Labor Day. Not how I would have preferred it. But yeah, you got off easy this time. But that means there's a humongous scary exam the week after. So, there you have it. Title says abstract algebra still? Oh no. It shouldn't. Okay, good. All right. Okay, good. So, class, let's put this boring music on so that I can officially begin. Oh, good to see 19 of you here out of 33 people in the class. And that's great. Great attendance. Good job. So, that's done with. I'm done with that little piece of garbage news. Okay. What are we going to do today? Final little comments on trig substitution so that you can do your homework completely. And then we'll begin partial fractions. The next trig, the next integration technique that I teach you, right? Okay. So, what is loose ends? So we know the basic strategy in trig substitution. I had passed around a memorandum. Now there's 19 people here and most of them are not even in the class. So apologies to those of you who are not in the class. All you will see is a blank screen because this is classified what I'm about to show. So I apologize. But for the 5 people in my class that are here, remember, we have this. The method of Trig substitution. Yeah, you gotta use these 2 identities to motivate a substitution. And then you move to the theta world. Hopefully, the integral is gooder. It's gooder than the one you started with. And then respect the person. Respect them. They came to you with x's. Give the answer back in x's. And how do you do that? You witness the original substitution with a triangle. And then you complete that triangle. So we saw that. I went over it so many times. But there are some situations where it doesn't look like it's perfectly positioned for a trig substitution, even though with a little bit of massaging, you can get there. Right? That's like, what if there are some weird numbers? Okay? What if there are some weird numbers that slightly put a wrench in the general plan? That's all I'm going to talk about. That's the final note that I want to end on. So for example, here's a typical example I want to go over so that Math Mama can do their homework. Okay. So look at this thing. This thing rhymes with arctan's integral. This thing rhymes with but it's not exactly the same. There's these silly numbers, these coefficients. Okay, so let me show you what you can substitute in order to get around to sort of deal with the little numbers that might show up here. Okay. All right. So let's do this. So the motivating idea is, yeah, draw up tangent's fundamental identity with its relationship with secant. Yes, this is still good, right? This is, even though it's Friday, it's a different day, but that wasn't good. There was, just because it's a different day doesn't mean that the identities change, but they're same throughout every day. That's still good, except doesn't look completely relevant to us. So what you want to get to is first focus on getting the number right. So like what we're going to use is like this idea. This is the sort of place where we want to end up. All right. So what you do now is you carefully substitute x equals something times tangent so that you get to this right-hand side. Okay? So that's like where you aim for this. Okay, so that's basically what you try to do. You try to aim for that side. Okay, so here's how you do it. X equals, if you just did tangent theta, like you normally would with the integral that rhymes with this one, that's not going to get you to 25 tan squared plus 25. It's going to get you 36 tan squared plus 25. So what you do is you place 5 divided by 6 in front of it. Why? Because of the following. Why do you do this? Why the 5/6? So that when you stick this in, because you're ultimately going to do that, so that when you stick it into 36 times x squared plus 25, right? When you stick this in, you will see that some great cancellation happens. 36 times 25 over 36 times tangent squared theta. I'm just squaring this and squaring that. And so then this thing just perfectly aligns. And you get 25 tan squared theta plus 25, which is just one thing instead of the sum of two things. Okay? So this swoops in. So you got to learn from this example that what you do is you modify tangent with a little bit of a fudge factor. And which one? You're guided by the square root of 25 and the square root of 36. That's what was the essence in this problem. All right, so let's execute that real fast to see how it can take you all the way through. All right, let's do this. So I was just trying to show you how to get to this slightly modified dream situation. And the path to it is a 5/6. The 5/6 trick, that's what we'll call it. So then you have to differentiate the substitution if you want to actually convert everything into thetas, into theta world. How do you do this? Derivative of that is 5/6 times the derivative of tangent, which is secant squared, as we've at this point just memorized, but it's just the quotient rule. Okay, now transform. Transform. Okay. How does this integral look now? It'll look like, wow, wow, wow. Okay, you're gonna put x in, square it, multiply by 36, add 25. But we know that the end result will be 25 secant squared theta. That's how we kind of arranged it. That's how we arranged this careful little 5/6. Okay? Dx gets replaced with this. Incredible. Because look at that. That's incredible. Huge. Huge cancellation. A little bit more even. There's even a little bit more. A little bit more. So you get this, 1 over 30. Now chat, all 26 out of 33 students, many of these 36 not even in the class. Okay, what's the next thing you do? What do you do when you're at this place? Respect. Rack 1336, just a human guy. Chisonen. Hey, Chisonen. Hey, Chisonen. Maybe you should stop playing Just Cause 3. I can see that you're playing Just Cause 3. Maybe pay attention to class. All right. So let's do this. Respect. Okay? Yeah, I know it's open, and I know you're playing. Yeah. Switch screens. Time to switch screens. Just own in. All right, respect. Let's go. All right. So we gotta unwrap the theta. Unwrap this thing. Unwrap it. Okay, where is it? It's over here. Wow. Okay, isolate it. Isolate it. Okay, keep going. Put it all over there. Incredible. Incredible. So, what does this say? This says, so let me write it. So all together, you have 1/30 arctan 6/5 x plus 9.444445433332. Could be anything. It's indefinite. So I don't care what the exact answer at the end was. What I want you to pay attention to is this fudge factor. Fudge. Now, the fudge looks different in different problems. So don't just focus on 5/6, focus on the motivating idea. The motivating idea is, okay, maybe you can't get to tan squared plus 1 equals secant squared, but maybe you can get to a multiple of that identity. In this case, 25 times it on both sides. And that's the sort of underlying neurons firing in the left hemisphere of the centripetal lobe.
Yes, science!
Okay, now I'm going to do another problem, just real fast for you. Okay, what I want to do actually, I want to hear from Chisonin. Okay, Chisonin, who is playing video games, I want to hear from Chisonin here. Let's see. You'll see the effect of video games. Okay, Smash Time Fools redeem juggle. I will juggle at the end of class. Thanks for redeeming it right here in the middle of lecture. Wonderful timing. But Chisonin, I'm gonna go to Chisonin here and get in Discord. So Chisonin, using the mic that I know you have because you're playing video games. So yeah, take that mic and use it and join me in general. Okay? Okay, Chisonin. Chisonin. You gonna join?
Hi.
Okay, hello. Hello, Chisonin.
Hi. What's up?
Okay. So, why don't you tell us how to do this here integral?
Let's see. Judging by the look of it, I would probably start out by deciding to use tan squared theta plus 1 equals secant squared theta.
So you would dive right in with a trig substitution.
No, that's just what I would choose to use. But yes.
Oh, no.
I squinted at it.
Okay, you squinted. But what would you do if you were not forced to choose a substitution?
We definitely want to get whatever's going on at the bottom to be simpler.
Okay. All right. You've got some people in chat, like Hot Tamale is saying he's in for it now. So people are afraid for you. That's interesting. Okay. So you're saying you would just dive into a trig substitution here. Is that right?
Yeah.
Okay, you want to go? No. You want to go there? Let's go there. Let's go there. This will be a learning experience, mostly for you, because everyone else knows that's a terrible idea. But for you, it's going to be very educational.
Okay, good.
Lots of F's in chat. Yeah, people see the F. Okay, Ready? What should we write as our substitution? Motivated by the last example. Here, let me scroll up for you. This one had 5/6 tangent.
I would say 7/6.
Okay, let's go with that. 7/6 10. Brilliant. And dx is therefore what?
It would be 7/6 secant squared theta.
Good, d theta. Good, fantastic. Okay, so let's see what happens when you substitute x into the bottom. You get 36 times 7/6 tangent theta all squared plus 49, right? And then for the same reason that everything worked out nicely last time, you get 49 tan squared plus 49. Do you agree?
Right.
Okay.
Yes.
And this you can trade away for what?
For the bottom of the right.
Yes.
The
Okay.
integral.
Yes. Absolutely. So you're gonna go and transform. Awesome.
Yeah.
Okay. And so okay, the top. Hey, is the top? Let's look at the top real fast.
Yeah.
Hey, it's exasperating for everybody. Okay. All right. So what's happening in the top?
I'm not really sure what to do with the top.
Yeah. It doesn't. It's not like.
It's not nice.
It's not nice, right? Not nice. If only we could like strap like a rocket or something to this thing, like from Just Cause, right?
Yeah, that'd be nice.
Like a video game, like and then like a F-39 rock plane just like intersects it and just takes it away with like strings. Isn't that what that game is?
Yeah, pretty much.
If only this
That's
part
it.
would just kind of rocket away, yeah, with just like that game you are currently playing right now. I know you're playing, right? That's the difference. It sucks. This part is a bigger complication than what happened last time. Do you agree?
Oh yeah.
Yeah. So that is a problem with this example, but I want to tell you that ultimately this little thing, this thing can be dealt with. All right, so if you keep pushing through with the trig sub, you will get to the other side. One thing I want to mention though, just while we're here, is the trade-off here, 49 tangent squared plus 49 trades off perfectly for 49 secant squared. So that's what goes in the bottom here, right? And then d theta dx becomes 7/6 secant squared theta d theta. So I'm saying you can keep going from here and you'll get somewhere. It'll be a little bit painful, but you can get somewhere this way, okay? So what I want to discuss with you is an alternative strategy. And what is that special different move? So let's do a different move. This different move you'll use a lot next week. That's why I want to bring it up. Okay, so our integral was 3x plus 1 divided by something garbage that looked like a trig substitution. And what you do is you split this up. Split it up into two parts. Do you know how I'm going to split it up? Chisonin?
How?
You don't know.
No.
Okay. Can you try to predict?
I'm just gonna split up. I can't think of the word, but split up. What's on the bottom?
When you have a fraction and it has a plus in the bottom, is it easy to split that up?
Yes.
Like a over b plus c? Are you inclined to believe that this is a over b plus a over c?
Yes.
Okay. All right, so just remind me to add this to the wall of shame. All right, we got to add this to the wall of shame. All right, everybody in class, remind me to add that, because I think what you're remembering, Chisonin, is b plus c divided by a fixed denominator is split upable.
Yeah, that makes sense.
That's actually true. Yeah? You need to have a common denominator in order to add fractions just on the top. B plus C equals that. Yeah? So that's how I'm going to split this fraction up. The only way that you can split additive fractions up is if you add with the same denominator on both chunks. Okay, so that's how I'm going to split this up. Like this and like this. All right? Let's do that. Let's make two integrals. 3x plus 36x squared plus 49 plus 1 over 36x squared plus 49. And now what I'm going to ask you is, does this integral look similar to an example we did earlier in class?
Yes.
Yes, that looks pretty much the same
Yeah.
as this one, right? But with the 49 instead of 25. So you can go, and this trig sub gets you there pretty easily, right?
Yeah.
Okay, so this, I'm just going to label it as trig sub. And it's x equals what you said, 7/6 tangent theta, or whatever. It's a fudge factor trig sub. Yeah?
Yeah.
Okay, but I want you to now look at this one carefully. Is there something about this which looks friendly?
Not really.
Not really. Okay. Okay. So.
Well, it can be simplified, right?
How would you
No,
say?
I can't.
No, right? Yeah, it's hard
No,
to
I
simplify
can't.
it because the bottom is a very big
Yeah.
power. Yeah. But what do you notice about the relationship between like this whole bottom and basically this top? Let me change. Let's do some pretend, Chisonen. What if this 3 was a let's say 72?
Yeah. Yeah, I don't know. Drawn a blank.
So the bottom, if you differentiate it, you would get the top.
Oh, okay.
Is that true about this one in relation with the top and the bottom there? The other one? No, it's not, right? Okay. The fact that this is a 3 here is not concerning in this situation because we'll just have a little bit of a division at the end.
Right.
Okay? So what that suggests, the neurons that motivate, what that should fire in your head is what?
You should differentiate the bottom.
Yeah, so what is the name of the technique that when you see one part's derivative happening elsewhere in the integral up to a number, one cordoned off part whose derivative also happens in the integral, you can sort of cordon that part off. What is this technique called?
It's not substitution by parts.
No, it's just substitution, right?
Yeah, it's just substitution.
Just substitute. Just substitute. And the substitution will be u equals what?
Is it just
The whole bottom.
Is it just the whole bottom? 36x squared plus 49.
Yeah, absolutely. And so what is du?
72x
dx, right?
Yeah, dx.
And so here's the point. Look, x dx, which is like the essence of this quantity up to constants, it's right here. X dx right here. See that?
Mm-hmm.
So let me isolate that for you. 1 over 72 times du equals x dx. Do you agree?
Yes.
So now I can translate everything. Translate to u. So I have 3 times x dx, right? So 3 times this 1 over 72 times du. And that's divided by, what's the bottom?
36x squared plus 49.
And what is that when you translate into u's?
Is it just 36u? Or is it that the derivative of it?
Well, 36x squared plus 49. Do you see it right there in a rectangle?
Oh, it's just u.
There we go. It's you. You've got it. It's easier than you think. All right.
All right.
So here we go. Now this is a number. I don't know what that number is. 3 over 72. Karen. $24? 24? Yeah, 1 over 24 times 1 over u du. Integral. Yes? I just brought the numbers out.
Yes.
Yeah? Okay. What is the integral of 1 over u? You recognize that?
Yes.
Okay. Just type it into Wolfram Alpha. No one can hear you. What is that? You should know this one by sight.
I'm struggling to remember.
It starts with a, okay. It rhymes with natural hog.
Natural log.
Okay, good. That's good. This is 1/24th ln, and then there's this little absolute value that you put in. Okay. Yes, it's pog natural. That's the language you speak. So Sparky from Clash Royale tells you it's pog natural or natural pog. Okay, so that's how you can remember this. All right. Okay, this whole experience actually. Okay, so now you respect, yeah? Just respect them. What is u? U is 36x squared plus 49.
Mm-hmm.
Plus c. Fantastic. So this is actually, as you definitely agree, it seems, this part is easy. It's old school. It's not trig substitution. You don't need a trig substitution to crack this part, and only this part is the part that actually sort of requires a trig substitution to get through. So that's the trick. That's what I'm trying to emphasize in this example. That just because you have something squared plus a number doesn't mean you just automatically dive in and just do a trig sub. Carve out some of the old stuff you can do, set it aside, and then only focus on the part that actually requires a trig sub, and so that way you're not doing too much. You're not going down a scarier path. Okay? That makes sense?
Oh yeah.
Okay, yeah. All right. Go practice. Okay, you know what? Now that I've talked to you, I think I understand you a little bit better. So we're gonna have to, I'm gonna have to tell you something now. I have to give you some instructions for improving. Let's see. Okay, so let's see. This is specific. I'm gonna give you a prescription real fast. I am a doctor, so but not a real one. So as you can see on the bottom, I'm not at all a real doctor, but okay. So for you, I would recommend a bunch of ordinary substitution problems. Okay, and I would do that 3 times. No, actually, I would do that 10 times every other day. Okay, so ordinary substitution means like u equals blah. Blah x, blah, blah, x, blah, 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 x. Yeah? All right, and do that 10 times every other day for the next week. 1 week. And treat it like a game. Treat it like a game. Like Just Cause. 3. Okay? Okay?
Alright.
Alright. Yeah, good. This is your thing. Just practice ordinary substitution. Because right now we're focused on trig, but then I don't want students to just think every time I see this, it has to be a trig sub. No, it can be a combination of old school stuff like this, plus the essential part, which is a trig sub. And that'll get you there quicker. Okay, thanks for participating. Go back and switch screens. Okay?
Okay.
All right,
Thanks.
see you. Yeah. Okay, get out of here. All right. Okay, class. That's awesome. Good, yeah, Chisonen killed it. That's right. He definitely crushed it in the sense that he ruined the lecture because it was just a real bummer. But yeah, he definitely killed it. Yes. Thank you, Chisonen. All right. Okay, so now I want to begin the discussion on partial fractions. Okay. Those Chisonen, those could be related. I'm not sure, but there might be a little bit of a relationship between those. Just, I don't know. Maybe. I'm not sure. Okay, so let's go. Begin partial fractions discussion. Ready? Let me tell you what partial fractions is. What? Write this in your note cards. What is it? It's a method for dealing with integrals of what are called rational functions. Oh my god, Gath Weigel has redeemed Teacher's Pet. Everyone check out Gath. She's a organic chemist and an explainer of all things. Wait, that shout out did not work out, but that is one of her emotes. That's Hamilton, her dog. So that didn't go well, but it's a method. So what is partial fractions? It's a method for dealing with integrals of rational functions. Now I know my students, they don't believe in just fancy talk, right? They want to see results, not fancy talk. No ivory tower garbage. What's a rational function? It's one polynomial divided by a second polynomial, 2 polynomial. Look, polynomial, like this. Don't do inverse power. Don't do negative powers. Positive powers and numbers. Something like that, okay? E.g. How to? How? Now, I know. Right now, you're trained to immediately say trig sub. Because look, x squared minus 4. Oh, so I can do 2 secant theta. As you'll see, you don't always have to do trig sub. In fact, in this one, you don't. You don't need it. What the key is your ability to factor the bottom. So the key is going to be, the first key, your ability to factor the bottom. Okay, so we're going to learn how to deal with this one, for example, or in many others. Okay, many fractions. And what's the real underlying motivation? It's this. Which expressions should we not be scared of? Which ones can we actually solve? And the point of partial fractions is to teach us that these are all in principle, these are doable. That's the lesson of partial fractions. But how? How exactly are they doable? Okay, so here's an example I'm going to show you. Here's an example. All right, one example is silly. For example, this fraction. We can integrate it by trig sub, or now you've probably memorized it. This is arctan. Done. That's a particular fraction. One polynomial, a constant, divided by another one. Notice how the bottom doesn't factor. Just notice that for now. Thing didn't factor. So now I'm going to do an interesting example. Here's a more interesting example. So this my example is going to start backwards. All right? So let's see if I can do it. I'm going to add these two fractions. All right? We're going to go back to kindergarten. Go back to kindergarten. Add these fractions. Add. All right? Let's do this. We do it. We go. Look. Now, you got to find a common denominator and all that stuff. Okay, so you multiply top and bottom by x plus 1. And then this one you multiply top and bottom by x minus 1. So that, Chisonen, so that you get the same denominator, so that now I can absorb them. Yeah, now I can add them over the same denominator. Chisonen. Good. And so you get, add these up. Yeah, let me just do this example. Let me just do this example. You add those up, it didn't go as planned. Add those up, and you get 2x divided by x squared minus 1. I multiplied these. This example did not go as planned, so I'm going to zip through it. In other words, let's just keep going with this. In other words, just file this away as a complete tragedy. In other words, if someone asked you to do this integral, yeah, and if you just were really good with fractions, you'd be able to replace it. If you knew how to go backwards, you can replace it with two other integrals. Everyone's laughing. Who knows what I did wrong? Everyone's laughing. Okay, so just, if you were given this integral, and if you knew how to add fractions, like backwardsly, if you knew how to crumble a fraction into two fractions, like this, you would have the power to split this integral into two easier integrals. Why are they easier? Let's just go with it. Because this is clearly natural log of x minus 1. This integral, this whole integral, is immediately natural log of x minus 1 by a simple substitution u equals x minus 1. The du part is just dx, so there's no extra fun. And then this part is natural log of something else. So you can just immediately, with vision, see these simpler integrals as natural logs. Let me do another example, a third example. Similar, but not the same. This time I'll get it right. What if we subtract these two? There we go. Let's subtract. Let's subtract these two fractions. Okay? Let's go ahead and cross multiply and okay, so x plus 1 over x minus 1 times x plus 1 minus x minus 1 over x minus 1 times x plus 1. And then you do the math. Now there's a minus sign, so the x's cancel. And then I have 1 minus negative 1, which is 2. And the bottom is x squared minus 1, difference of squares, that FOIL it or whatever. Okay? So, in other words, if you go back and you do this subtraction of fractions, you will get this fraction. All right? But now check out the fundamental idea here. The fundamental idea is to ask the backwards question. So, what if someone asked you to integrate 2 divided by x squared minus 1 dx? What if we had to integrate this thing? Well, one thing you could try is some disastrously painful trig substitution. It's in that ballpark. You could try that and you'll get somewhere crazy. All right. But there's an easier way. The easier way, if you know how to do it, which is what we're learning, partial fraction decomposition, if you know how to go and get back to that world, if you know how to trade your current integral as a sum of simpler fractions, those two, you can swap away. You can, with the right magic, you can trade the integration problem in for the difference of these two integrals. If you know how, if you've been taught the magic of partial fractions. Okay? And now look, just visually, by sight. Okay? It's true. If you did the trig substitution, the one that you think you should do, and then did some respecting at the end, you would get to this end result. But it would be much more painful than just magic. Right now, the magic is obscure. How the heck do I know this is exactly how 2 over x squared minus 1 decomposes? How do I know this decomposition? This splitting up? Just by divine inspiration? No, there's a method. We will learn a method of decomposing a fraction like 2 over x squared minus 1, e.g., into the sum or difference or whatever, into a bunch of simpler fractions. And this method is called the method of partial fractions. It's like you took a fraction and you broke it up into partial fractions that are little parts of the big fraction. I'm just making up a reason why it's called that. Method of partial fraction. Sometimes partial fraction decomposition. I decompose a complicated fraction into a sum of easier fractions, which are easier on my eyeballs to quickly integrate. Okay? Good. So that's the introduction to this technique. How to deal with integrals of ratios of polynomials. The underlying secret will be how to crumble fractions into simpler fractions. And then the simpler fraction integrals are doable very quickly, now that you're a master of substitution, for example. Chisonin. Okay, done. That's my lecture for that's what I needed to cover today. I now look at chat. Let's see what went on in this crazy chat. Okay. Oh, thank you, Recur. Thank you, Dr. Derp. Thank you, Calc Math. Thank you, Monto Nerito. Thank you, all these people. Grav 48. Oh, that was 2 hours ago. Okay, so people are redeeming things, juggling. Okay, so I owe some things. And let's see. Ice Scaler, that is 100% true. That the confidence part is a big part of getting better at math. But there's another part that is underappreciated. And that is that the student is not especially bad just because they're having trouble immediately with the problem. There is a certain amount of trauma that everyone has to face before they become good at that thing. And if the first instance of trauma, you assign them an F grade, and then there's no follow-up, like, here's how you could get better. Come to office hours, do this, work one-on-one with a student or whatever, early in the education. If the message is just, oh, you couldn't do it just right away after reading the thing, then wrong. If you're not given time to deal with the trauma, that has to be dealt with. There's no way of cleverly organizing the classroom. Let me put this number line here, and then let me make a little note card there. There's nothing that you can do to substitute for the raw internal trauma that has to happen in the learning experience. The feeling of like the ridge is forming, it's fundamentally traumatic. It's like something unnatural happening. It's not just grunts and obvious things anymore. That has to be felt. And students should realize that they are not usually they're not uniquely bad. That yes, your professor felt that and was encouraged at the right moment, but they did feel it. They did feel it. They might have forgotten that they felt it, but there was a moment when they did feel it. And that's normal. That part, I'm very afraid, is being minimized by people who think they can just magic away that part of the learning experience by flipping the classroom 180 degrees or something. I don't know. Whatever. Okay. All right. But that doesn't change what you said, Ice Scaler. There's a thing. If you just slap an F grade right there at the first moment when the person felt friction, yeah, that's terrible. Like, that's too blunt. It's too blunt of an instrument, especially at a younger age where it's like, you're just trying to figure out how to be, Anyway, let's see, what else? FS Roosta, yeah, 12 hours, 17. Hey, FS Roosta. Do you know any other jokes, or is that the only joke you know? I'm just asking. I mean, I just want to know. I just want to get to know you better. Do you have any other jokes, or is that it? Let's see. Oh yeah, special thanks to Chisonin for, turning the video game off and participating. Good. Special thanks. That was okay. Gath is technically the teacher's pet, but teacher's pet number 2 is Chisonen today. So Chisonen, you earned it. Go back to flying rocket ships into jets, and then just insane physics, crazy video game. Okay, Chisonen, go do that. But you know, remember the doctor's orders. This was just for you. Here, let me. If you forgot it, Chisonen, here's what I prescribed for you. Ten problems every other day. 1 week. Treat it like a game. Chisonen, you wrote it on your note card? Yeah, you're getting it. You get how much I love the note card, people. Awesome. Oh, what software do I use? There's a command for that, Silent Byte. I think so. Let's see. Is there a command? Meanwhile, I will give Tropical Geek their Shungite. Here's your Shungite, Tropical Geek. There you go. You might be overdosing on Shungite at this point because you redeem it a lot. So just be careful out there. Okay, I've got a juggle and a bike till heart explodes. Okay, let's do this. Let us juggle. While I'm juggling, class, I want you to think about 2 things. How to deal with the fudge factor. Where does the fudge factor come in a trig substitution? And then start asking, how the heck do you crumble a fraction into smaller fractions? As you can see, there is great utility if you have the skill to crumble a complicated fraction into a sum of simpler fractions. Maybe the simpler ones you can just do by sight. A quick U substitution, like Chisonen will become a master of. Next week, if you're ever thinking, hey, this problem might require just an ordinary substitution, ask Chisonen. They will be a master by then. Okay. Alright, so next, I do this. Alright. Let's talk about where we are in the whole class. We will have roughly 2 more weeks of this integration purgatory. This hell of just pulling levers to crack a nut. We will be more conceptual after that. I will then tell you, what the heck were we computing? What was it? I'll remind you of that. I'll tell you about Riemann and his sums. Sums, not his children, his sums with an M and a U. Alright? I will go back to conceptual stuff, but only for like 5 seconds. Because then the rest of the semester basically is a topic, a fascinating topic, called sequences and series in particular. We will learn how to add infinitely many tiny things. And sometimes we'll get answers, and sometimes we'll get garbage. And we'll learn how to navigate that kind of mathematics. That's the second part of the course. That's the overall structure, where we're headed. We're still 2 weeks left of this purgatory. This integration techniques video game, if you'd like. It's just a game. It's just a bunch of flexing of this thing here. That's all we're doing. We're flexing. We flex this thing. It's like going to the gym. That's it. All right. Nice sandals. Thank you. Okay. Are there recordings of the office hours? No. No. You should just come to office hours. Are there recording? Can you show me how? Wait, but Battlestar Galactica, you did come to office hours. Okay, good. Yeah, more people should come to office hours. Can you show me how to find the zeros of a polynomial? By the... Oh. Oh. Yeah, electric nature? Yes? I can. But hold on. Let me see if there are any questions from, like, my class. Okay. Okay. Okay, this was a good chat today. We didn't have any weirdos. Man, we had some weirdos the other day. It was crazy. But this is a good day. Okay. I just need a pipe. I just need a pipe now. Yeah, actually, we did 3D print a pipe, Dr. Derp. But then I wasn't sure if that was legal to show myself with a 3D printed pipe. Just as a prop? Yeah, I know. Okay. Totally legal? Oh, yeah. I'll just believe you. Yeah, but is it legal to do that in front of your students, Dr. Derp? I don't know. These days, I don't know. Everything is just riddled in tape. Okay, let's see. Okay, there was a question. By Electric Nature. Hey, Electric Nature, are you still here? Otherwise, I won't address it. Electric Nature. Shungite? Wait, I gave you the Shungite. Tropical Geek, you weren't looking. So you have multiple tabs up, and you're probably somewhere else, watching someone else. Caught you. I caught you. Okay. I have a clip? Oh, please don't clip. Okay. Hey, Electric Nature, are you here? No. Okay. So I'm gonna assume you're not here, but maybe you can ask their question next time. Oh, you're still here. Okay. This P over Q thing. Thank you, Electric Nature. Okay, this P over Q thing. Okay. So, this P over Q thing is called the rational roots theorem, I believe. Don't take my word for it. It's called the rational root test. Maybe it's a test. Okay, so what does it say? What does the rational root test say? Hold on. Okay. Email. So what it says is it gives a list of candidates of roots, rational roots, fraction roots. roots of a polynomial which has integer coefficients, let's say. Coefficients. And I gotta remember it now. Okay, so here's what I remember. Okay, so if you have a polynomial, A, B, C, D, E, F, G, H, I, J, K, or all these are integers, integer coefficients, integers. Then, if this has a rational solution, which it might not, by the way, electric nature, it might not. So, but if it does, then, if it has rational solution, let's write it as m over n. Then the solution is in the following finite collection of cases. Then m is a factor of k, the last coefficient, and n is a factor of a, the first coefficient. Let me make sure I got that right, because I'm old. Okay, just watch how I check this, because it might be what you're wondering. Like, maybe you just have a hard time remembering exactly which is the numerator and which is the denominator. So here's how I'll check it. I'll check it on 3x minus 2 or plus 2 equals 0. Okay, why do I want to check it on this? Because I know a rational solution to this. It's 2/3 or something. So x equals negative 2/3. Now I'm going to check. Okay. 2, negative 2. Yeah, that factors into, that's like a factor of this part. And then the 3 is a factor of this is a factor of that one. Good. So there's two ways that you might get this flipped around. Like, oh, are these supposed to go as factors of the last term, or are these? But the top one is a factor of the last, and the bottom one is a factor of the first by a quick, stupid example. Okay? Great. So for example, let me do another example. Like, wow, you have some crazy cubic polynomial that you don't know how to solve. Okay? Okay, and they ask, question, does this have a rational solution? Not some weird solution with square roots and cube roots. No, just fraction. Okay, well, thanks to the rational root theorem, we can just check. We can check 12 possibilities. Okay, so check. M over n, where m goes through all factors plus and minus of 2, and n goes through all factors of 10. Okay, so how big is our list? Plus and minus 1/10, plus and minus 2/10, plus and minus 2/5, plus and minus 1/5, but that's 2/10. Okay, so 6. Okay, 6. 6. Oh, plus and minus 1. Don't forget that one too. Plus and minus 1. Oh, yeah, plus and minus 1/2. Oh my god. Okay, all you have to do is check these 10 cases. This, if it's there, it's among these. Okay? So just plug them in and see if they work. And that is the magical rational root test, or rational root theorem or something. All right, electric nature. Okay, and everybody else just sitting here. Ice Scalar, thanks for following. And that's it. Okay, so now I should get out of here, really, and go peer review that paper. So I better get out of here very fast. Okay, who's out there? If you list the roots first, if you list the factors, yeah, the factors, yeah. the factors, yeah, I agree, absolutely. There are many ways of not making my kind of mistakes, but the essential theorem is this. The essential fact is this. And you use uniqueness of prime factorization to deduce this theorem. The simple uniqueness of prime factorization type argument. Okay. So where can we go, folks? Hey, is Gath out there? Gath. No. Is Melko? No. Who's out there, folks? Oh, 1? That's kind of a long way away. Who's out there, people? Who do you think is a good person to... None of the usuals? None of the usuals. Gath. Boy. Okay, well, I guess I'll just send you wherever you want to go. I guess I'll just do a hard screeching halt. Who's Makey? Who's Makey? I don't know if that's saying it right. We've gone to the Paul place, but describe the Makey? Oh, delivery guy in New York? Oh, that's cool. Yeah, let's go there. Let's just go there. That sounds fun. That sounds really cool. Okay, let's go there. Makey. 860 people watching? Okay. Okay, well. Okay, fine. Let's go there. Let's go there. I mean, it doesn't even matter. I don't even have to tell you to respect or anything. It's just no one's gonna know that we're there. Oh, okay. He's one of those. Okay. Yeah. So we don't even have to be respectful because no one's gonna know that we're there. So good. Great. Get that inner troll out. Okay. Makey it is. Ready? Here we go. Start. All right, let's go check this out. This is probably really cool. This is gonna be cool. Okay, bye-bye.